Hey everyone, so we're going to do amines naming and structure again, since the last video was uploaded without any noise, with audio. And so basically what we're going to be talking about with amines is the naming and classification of amines, the structure and properties of amines. That'll be what this lecture is on. Then we'll talk about the basicity of amines and aryl amines, it's supposed to be one word. Biological amines, Henderson-Hoppenbach equation, talking about the protonation state of amines in different pH solutions. The synthesis of amines, which will be some of that we've seen before through reduction mechanisms. Reactions of amines, so when you start with amine and go to something else. Reactions of aryl amines, which is going to be similar to a nucleophilic aromatic substitution because a lot of aroamines are aromatic, heterocyclic amines, and then the spectroscopy of amines. Okay, so let's get into the naming and classification of amines. So naming an amine molecule where the amine is the highest priority functional group, and amine is going to be behind carboxylic acids. So COOH, COH, and CO are all going to be greater than amines. And so where it is the highest priority functional group, we replace the suffix with amine, right? So it's a pretty straightforward naming convention. Um, if we have something like this, NH3, this could be ethyl amine, so you can treat it as a R group, or we can also name this ethanamine, or you just replace the E with amine there. So both of those are going to be acceptable. When the amine is treated as a substituent group, so it's not the highest priority group, we call it an amino group. So if we had something like propanoic acid here, and we had an NH3 on the second carbon there, this would be 2-amino propanoic acid. And so those are the two ways that we name the amine, if they're a substituent group or if they are the primary functional group on the molecule. We can classify amines according to the number of R groups that are attached. So if we have one R group, that'll be a primary amine. If we have two R groups, that'll be a secondary amine. And if we have three R groups, that'll be a tertiary amine. So these are the different a tertiary amine. So really it's just the number of alkyl groups that are bonded. So this is kind of conversely to what we see with alcohols, or it depends on the carbon bonds attached to the carbons that the hydroxyl group means. It's directly their R groups or alkyl groups that are named. If we have symmetric secondary or tertiary amines, so that would be amines that fall into these two categories, meaning that these R groups are going to be the same R group, then we just have to add a prefix. The same way for ethers, if we have dimethyl ether or something like that, it would be di or tri, respectively. Right, so something like this and something like, not enough room to draw here, I'm gonna do this one better. That would be dimethyl amine and triethyl amine, respectively. Um, Asymmetric secondary tertiary amines are called N-substituted amines, and we use the largest R group as the parent chain name, right? So if we had something where we have a propyl there, an ethyl, and a methyl, these two groups right here are the N substituents, and this would be the parent chain for the amine. And so we would say this is N ethyl, N methyl. So we list these in alphabetical order, and then it'll be propanamine or propylamine. So both of those would be acceptable, right? So we call them N-substituted and N-substituted amines when they're asymmetric, right? So this is for asymmetric and this is for symmetric amines. So that's how we name and classify different types of amines. Let's go through a couple of examples of how we do this. We see on this molecule, we have a carboxylic acid group. So that'll be cyclohexane carboxylic acid. And then we have to name the amine group as a substituent group here. And it's on the fourth carbon in the cyclohexane. Sorry, the third carbon. 1, 2, 3. And so that'll be 3 amino carboxylic acid. So I'm just going to move this a little bit closer here. So 3 amino cyclohexane carboxylic acid. And this would be classified as a primary amine if we were just classifying this amino group here, because it only has one R group that's attached to it. On the second molecule, we have an aldehyde. We have 1, 2, 3, 4, 5 carbon atoms in this chain. So that would be pent as our parent name. Pentanal would be the parent chain name. And then we have an amino group, and it's a substituted amino group on the 1, 2, 3, 4th carbon. So this would be 4NN dimethyl amino pentanal. Right, so we have 4NN dimethylaminopentanal to label both of the substituents group there, and have the symmetric. So we have the two uh, N. It's an asymmetric amine total, but there's two of the same group, so we have to have a prefix there. So that's why you have di there. The third one, and also we would classify this as a tertiary amino group because it has 3 R groups there. The third one is going to also be a tertiary amino group. And we're going to use the longest chain, which is going to be the isopentyl chain. So we can have isopentyl amine, or we can also call this 3-methyl butanamine. Both of these would be okay names for the parent chain. And then we have the two other groups that we'll list in alphabetical order. We have isopropyl and methyl, so the methyl is going to go first. So we have N-methyl and isopropyl, isopentylamine, or 3-methylbutanamine. Right now, those would be both acceptable. Then we have the last one, which we've already seen, which would be a primary amine, and this would be ethylamine or ethanamine, and both of these would be acceptable. So those are some examples of how we can name and classify different amines. Now we'll get into the structure and properties of amines. So amines are going to be sp3 hybridized with 3 different alkyl R groups and can be considered chiral centers. And so this would be and with 3 different L groups, they can be considered chiral centers. And so this sp3 hybridizations, we have 3 bonding pairs and 1 lone pair that exists in the unhybridized sp orbital. But what can happen with amines is something kind of interesting. So these chiral centers aren't true chiral centers because we get something called pyramidal inversion. And so with pyramidal inversion, we basically get rapid exchange between both chiral forms. And so what happens is there's a temporary energy barrier, which is about 30 kcal per mole, and we go into an unhybridized state, right? So the lone pair now exists in these unhybridized p orbitals, and it's a trigonal planar structure. And then we get a recreation of the sp3 hybridization, and the lone pair goes back in the unhybridized or the hybridized sp3 orbital. But if you notice, now that we've done this, we've taken and made the chiral center or the chiral enantiomer of this amine. And so we get inversion, which just happens at non-zero temperature, right? So this happens at at non-zero temperature. So this only happens at non-zero temperature, but everything in the universe is non-zero. And this exchange roughly the same energy as rotation of a carbon-carbon bond, right? So alkyl groups, you can rotate around this bond relatively freely. And this energy for this pyramidal inversion is about the same. So this happens, quite frequently. That's why we don't have a true chiral center for amines. We get this temporary sp2 hybridized structure, and then we invert the structure. So the sp3 hybridization goes on the other side. And we reduce the parity of that, or change it, reverse the polarity, the parity, sorry, of that, of the lone pair hybridized sp orbital. And so they are chiral centers, but it's not a true chiral center because we get rapid inversion between the two. And then some other properties for amines, similar to alcohols, amines larger than 5 carbons tend to be water insoluble. Generally, amines less than 5 carbons are water soluble because they're polar. Right, so we think about just ammonia. We have a dipole moment there, so they're polar, and they're capable of hydrogen bonding with water. So that means they can be water soluble. And also another consequence of this is that they have large boiling points because of strong intermolecular forces. Right, so there's some other properties that we see in amines is the um, larger boiling points and their water solubility. And you can actually take advantage of this water solubility in combination with their basicity to purify amines from other compounds. And so we'll leave that for this lecture. That'll be it for this lecture. And next time we'll get into the basicity of amines and arylamines because it's its own unique property that's worth its own discussion, especially once we start talking about amino acids and other biological molecules. So today we talked about the structure and properties of amines, how they can hydrogen bond with water to allow for water solubility. So that would be a hydrogen bond. And then we also talked about the naming and classification of amines. We went through a couple examples of that and how we would go about doing that for symmetric and asymmetric amines. All right, so that'll be it for today, and I will see you guys in the next section.